All right, let's talk about a force that's, well, everywhere. It's working on you right now. It's the reason you can walk across a room, why your car stops at a red light, and even how you can hold a pen to write. Yep, we're diving into friction. And trust me, it's way more interesting than you might remember from physics class. So think about this for a second. What's this invisible force that literally lets you walk, but also wears down the brakes on your car? It's kind of a paradox, right? It's our best friend and our biggest opponent, all at the same time. And that's exactly the story we're going to unpack today.
So, here's the game plan. We'll start with how friction can be both a friend and a foe. Then we'll get into the two main types, static versus kinetic friction. We'll even decode the formula behind it all. After that, we'll look at friction in action, take a peek at what's happening on a microscopic level, and finish up with the big picture, the unseen force.
Okay, first up, friend and foe. Let's really dig into this dual nature of friction. I mean, it's happening all around us all the time, so getting a grip on what it actually is, that's step one. So what is friction officially? Well, here's the textbook definition. It's a force that fights back against motion, or even just the attempt to create motion, between any two surfaces that are in contact. And the most important thing to get here is its direction. Friction always works parallel to the surface, pushing in the exact opposite direction you're trying to go. All right, to really get friction, you have to know that it's not just one thing. It actually has two main personalities, or characters, if you will. We've got static friction and kinetic friction. They sound kind of similar, but believe me, they act in completely different ways. And this table breaks it down perfectly. So on the left, you've got static friction. Think of this as stuck friction. It's what keeps things from moving in the first place. And here's the cool part. It's responsive. If you push a little, it pushes back a little. You push harder, it pushes back harder, but only up to a point. Then there's kinetic friction on the right. This is sliding friction. It kicks in once something is already moving. And the big difference? It's usually constant, and it's almost always weaker than that maximum static friction. Let's make this super clear with a classic example, the heavy crate. So imagine you're trying to push this big, heavy box across the floor. You give it a gentle push, and nothing. It doesn't budge. Why not? Well, that's static friction doing its job. It's like an invisible wall, matching your push perfectly and holding that crate right where it is. Okay, so you put more muscle into it. You push a little harder, then even harder, and then bam! The crate suddenly lurches forward and starts to slide. That little slip you feel? That's the magic moment. You've just broken through the maximum strength of static friction. And now for the really cool part. Once that crate is sliding, you'll notice something. It's actually easier to keep it moving, right? That's because you're not fighting that stubborn static friction anymore. Now you're dealing with kinetic friction, and, like we just said, it's weaker. This is why the hardest part is always just getting something to start moving. So this isn't all just guesswork. There's actually math to it. So how can we calculate this force and, predict how it's going to behave? Well, that's where the friction formula comes in. Think of it as the rule book for how friction works. It looks a little scary, but it's really just three simple parts. First, you've got F, which is just the force of friction we're trying to find. Easy enough. Second is N, the normal force. Don't let the name fool you. It's just how hard the two surfaces are being pressed together. So on a flat floor, it's pretty much just the weight of the object. And third, the really important part, that little Greek letter mu. That's the coefficient of friction, and it's just a number that tells you how grippy or slippery a combination of surfaces is. So, when something's already moving, the formula is super straightforward. The force of kinetic friction is just the coefficient of kinetic friction, that mu number, times the normal force. That's it. So a grippier surface or a heavier object means you get more friction. It's a really simple, direct calculation. And check out this table. This really shows how much that mu value can change depending on the materials. Take a look at rubber on dry concrete. That's a 1.0 for static friction. Super grippy. But look what happens when the concrete gets wet. It drops down to 0.7. That's a huge difference. Now, compare all that to bone on synovial fluid. That's inside our joints. It's an incredibly low 0.016. It's crazy slippery. And notice the pattern here? In pretty much every single case, the static friction is higher than the kinetic friction. Okay, time for a little pop quiz. Based on what you're seeing in this table, can you tell me why it's so much more dangerous to slam on the brakes when the road is wet compared to when it's dry? The answer's right there in the numbers. Go ahead, take a second and think about it. All right, let's move on from the theory and the formulas and see how this stuff actually plays out in the real world. We're going to look at friction in action, from something you do every day to something pretty amazing. We're going to check out 3 different scenarios. First, driving a car, where you want as much friction as possible. Then, skiing, where you want to control it just right. And finally, something truly mind-blowing, the movement of our own joints, where the goal is to have almost no friction at all.
Okay, and here is the answer to that quiz question, visualized. This chart makes it crystal clear. The grip, that kinetic friction coefficient, is just so much lower on a wet road. And since that friction is literally the only thing stopping your car, having less of it means you have way less stopping power. And that's exactly why cars skid on wet pavement. Now, let's talk about the complete opposite, where you want as little friction as possible. And the best example is inside our own bodies. Our joints, with their special synovial fluid, are ridiculously slippery. We're talking one of the lowest coefficients of friction ever measured, even lower than ice sliding on ice. It is an absolutely incredible piece of biological engineering. But what's actually causing all of this? Why does friction even happen in the first place? Well, to figure that out, we have to zoom in. I mean, way in. Let's pull back the curtain and take a look at the world on a microscopic scale. Here's the thing. No surface is truly smooth. Even something that feels like glass to your hand looks like a rugged mountain range if you zoom in enough. And friction happens when the peaks and valleys of one surface crash into and get tangled up with the peaks and valleys of another. So to move something, you literally have to drag those mountains over each other or just snap the peaks right off. And either way, that takes energy. And it's not just about the bumps and grinds. There's also some chemistry going on. The actual molecules on the surfaces can be attracted to each other, creating these little sticky bonds. It's called adhesion. And that's why the type of material is so important. The way rubber molecules stick to concrete molecules is just totally different from how steel interacts with ice. All right, we've gone from pushing a simple crate all the way down to the molecular level. So let's zoom back out and put a bow on this with one final thought about this powerful, unseen force. Think about this. In our own joints, we have almost zero friction, which is amazing. But out on the road, that friction between our tires and the asphalt is what saves our lives every single day. So friction isn't good or bad, it's just a tool. And the big question to leave you with is, where is it our greatest ally and where is it our biggest enemy? Think about that.